All right, gonna go over assessment 8 review here. Again, this isn't the answer key. This is your SI leader's answer key. So take that with how you may. Our first question asks us, that's chapter 7. Provide the rate law for an SN1 reaction. Okay, SN1 we know is two-step. That first one's going to be creating a carbocation intermediate, which is going to be our rate determining step. Therefore, it's going to be the only thing in our rate law right here. Okay, our starting material that our nucleophile is going to attack, aka our electrophile. Nucleophile is going to attack the electrophile here. It's going to create that carbocation intermediate. Make sure to include that rate constant, which is going to be dependent on what certain molecules are reacting. That will be the answer to number 1. That is the rate law for an SN1 reaction. It would be the same for an E1 reaction as well, because we get the carbocation intermediate. Number 2 asks, which species, singular or plural as appropriate, does the rate law in question 1 depend on? It would be singular, because we only have one thing it depends on. That's our carbocation intermediate. It asks for what species. So that makes me think probably the better term for this would be electrophile. Our nucleophile and SN2 is important. We get rid of the nucleophile, we're only worried about the electrophile here. It's going to create our carbocation intermediate. Okay. So I would say electrophile for number 2. Number 3 asks to sketch a free energy diagram of an exothermic SN2 reaction. Okay, SN2 we know is going to be one step. Everything happens at once, so we're only going to have one activation energy here. Okay, make sure to include energy on the y-axis, reaction progress, not time, on the x-axis. I have my reactants, my products. My products are lower energy because it asks for an exothermic reaction. I've included my activation energy here with this dashed line to get up to my transition state here. Okay, this transition state's where I'm going to get that hybrid where I'm kind of bonded to the leaving group and kind of bonded to the new group, the nucleophile. Okay. That's number 3 there. Number 4 asks why the following mechanism step is not reasonable. Briefly explain why this is the case. Here is kind of what we're looking at. Throw some products in there. We're really worried about the reaction mechanism. I forgot to draw in actually what causes that double bond to go up, and that is an OH molecule. Okay, so I see 1, 2, 3 species interacting with each other all in one step, trimolecular step. Chances of that are so small that we say that this is unreasonable. It makes sense that 2 molecules can collide in right space and time to then go through a chemical reaction, but for 3 to all do it at the exact same time is near impossible, so we say this is unreasonable. Good thing she did this in class just before. She threw a couple, I think she had a trimolecular and a termolecular steps up there saying they're unreasonable, so that was mentioned in class on Friday, that we can't have 1, 2, 3 species all react at the same time. Now this is okay to do, I believe. I mean, it doesn't look unreasonable to me if only these were in separate steps, but to show them all happening at the same time, that's a big no. Okay. Number 5, what is the major product of the following reaction if it follows an SN2 reaction? So we don't need to necessarily draw our arrows. We can, if it helps. I usually still do. Okay. Who has electrons or oxygen has a negative charge on it. Who wants electrons? This carbon here, because iodine is pulling electron density away from it. Iodine's a good leaving group, so that makes sense as well. What is the major product? I don't need to include iodine. I'm just going to go ahead and draw my major product here. Okay. Notice I have OH bonding, iodine leaving, so I need to draw OH. We need to make sure we care about stereochemistry here because it's denoted with iodine. SN2 we get backside attack, so all we need to do is flip that stereochemistry, and that would be our major product for an SN2 reaction. Number 6 is difficult, and I would have gotten this one. I guess if she doesn't do full credit, I probably would have gotten this wrong. This would have been my 9 out of 10 right here. I believe 9 out of 10. Again, I don't grade these. This is just how I go through it. All right. Chair structures. This was great. She brought this back, right? Okay. First off, I see I have an E2 reaction, so I'm going to end up making a double bond somewhere, and I need to worry about beta hydrogens. Okay. I also see that I have a pretty easily identifiable leaving group with fluorine. Okay. So I have, and it just says what's the major product. Okay. I have 2 beta hydrogens to choose from. Okay, and they're explicitly drawn in the problem, in the question. Okay. I can only choose beta hydrogens that are anti or paraplanar, syn paraplanar. Basically, like Newman projection, they were on opposite sides. It's easy to locate where they are in a chair structure. It's tough to describe. It's more difficult to describe this than show it. But basically, in a chair structure here, as she has it drawn, which is actually helpful in this case for us, is that the only hydrogens that we can take are those that are opposite in direction of fluorine. Okay? So if fluorine was going like equatorial this way, then if our leaving group was equatorial this way, then our beta hydrogen needs to be also equatorial, facing the opposite way. Here we have an axial fluorine, okay? And notice we have an axial hydrogen going in the opposite direction and an equatorial hydrogen going in that direction. So which one would be opposite of fluorine going straight up would be a hydrogen going straight down, okay? So we can only take this beta hydrogen here as our, the one that our base is going to attack. I had drawn both of them. If you drew both of them, I guess it wouldn't be full credit. This would be the one I missed as well. And only that I didn't identify that, oh, this one is syn paraplanar or anti-paraplanar. I'm just forgetting the term right now. Anyway, just make sure they're going in opposite directions from your leading group there. So my final product would look like I would get an intermediate. No, I wouldn't get an intermediate because it's E2. My base would come in and only take this hydrogen, creating a double bond here. And my major product, fluorine leaving, be a methyl group and methyl group. Okay. And I get a tri-substituted alkene there. All right. Number 7 asks to draw the product or products of the following E1 reaction. Okay. Now remember, E1, our leaving group is going to leave first, creating a carbocation. And when you can do a carbocation shift, do it. Right now I have a secondary carbocation. Is there anywhere I can do maybe a hydride or alkyl shift to make that a better carbocation? I could put it here in the benzyl position. That would be preferred. So take a hydrogen there. Hydrogen is going to bond to that carbon, moving the carbocation intermediate to that position. Okay, benzyl position is going to be much more stable. All right. Then we have our base that can come in and go ahead and take a beta hydrogen. It says draw the product. It just says draw the products of the following E1 reaction. Okay. I suppose you can get a double bond up there. So if we're going to draw all the products, we could take a beta hydrogen from up there, or we could take a beta hydrogen from down there. Okay. Notice if we take the beta hydrogen from up top, we'll create a double bond here. The carbocation will go away, something like that. Okay. and that's good because it's in the allylic position. Yeah, okay. This is the only confirmation for here, E or Z, because there's nothing on this side to really compare it with. Okay, so I would get that product there as one. Maybe the more likely product, it just says draw the product, so we're going to keep drawing these, would be this beta hydrogen. I would draw that, blah, 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 and I'd end up with a double bond in this position here. Okay. Notice my large groups are on either side. Okay, this would be the E alkene in this case of this conformation. And now I would also need to draw this in the Z. So this would be E right here. My large group on the left side of this alkene, my benzene is going down. On the right side, my large group, my ethyl group is going up to start. Okay. So then the Z alkene would just be moving that ethyl downward. Okay, like that. So long as this first line here is going down is okay. So I'm thinking maybe she wants 3. If you got the E and Z of this conformation, that's good. Again, I don't know how much how lenient she's gonna be with that. Okay. The big point is making sure to get the E and Z. Whether you took a beta hydrogen up here and created a double bond, it would be less substituted. So like it wouldn't be as good, but in the directions it just says draw the products of the following E1 reactions. So I think I ended up with 3 total. Double bond on the top and then the E and Z of our bottom alkene. Number 8, sketch a free energy diagram of the reaction from question 7. It's E1, so we know it's going to be 2 steps. We created, we had a good leaving group, bromine, okay, so that's okay. And then we also put an alkene in the benzylic position, which is also more stable, okay. So I made sure it was exothermic. I didn't write down everything here. This is just the general trend. I have my intermediate here with 2 transition states, okay? Cool. 1 activation energy, 2nd activation energy, reactants, products, reaction progress, energy. Last one, provide a reasonable mechanism in major products of the following reaction. The provided alcohol can react with aqueous sulfuric acid via an E1 mechanism. So we're told this is E1. If you're in SI Tuesday and Thursday, we did a couple problems where we made alcohol a better leaving group by making it water, okay? We have hydrosulfuric acid here, which I've drawn a little bit differently just to show that there's a proton we can take from it because it's an acid and proton donor. And we can make alcohol a better leaving group by making it water. Okay, it says in our directions that the provided alcohol can react with aqueous sulfuric acid, so that was a big hint there, to then make this a better leaving group, which we need for an E1 reaction, okay? So then, now water is a good leaving group and it will leave, creating our carbocation intermediate. We're provided with a methyl group down here, which is currently, I should draw that as a dash. Forgot to do that, okay? Now I can do a hydride shift here to move my carbocation in a more stable position. So let's do that. My hydrogen right up there, creating my carbocation now by my methyl group, okay? Now, before I always forget this word. Oh man. Bonded to, what's the geometry for 4 bonded things? Why can't I ever remember that? Crazy. Well. Trigonal planars 3, what? This is frustrating. Well, I'm bonded to 4 things. I don't know why I can't remember this. I have to look this up. This is not. I always forget this word, and it's used about every other week. Darn it. Tetrahedral. Gosh. Okay. So before we were tetrahedral, I always forget that word. Tetrahedral, I'm bonded to 4 things, and bond angle is about 109.5. I can explain it, I just can't remember what it's called. Tetrahedral. Before I was tetrahedral, and we could show stereochemistry with wedges and dashes and such. Okay. Now that we're trigonal planar, okay, we're flat, everything's in plane. Everything's in plane. All right. So the wedges and dashes go away when we throw a carbocation on there. And now everything is just perfectly in plane. It's a flat trigonal planar rather than tetrahedral, where we have something going out in front of us and something behind, wedge and a dash. Okay. So I had alcohol turn into water. I had water leave. Very common steps we'll get used to as we go. Okay. I also, because of this, lost hydrogen, and I made HSO4 minus. Okay, it's important. And then I had a hydride shift down here to get my carbocation on the bottom. Now, I didn't draw that as a separate step. It's probably better if you did. I ran out of room, and I just did the carbocation in its own step there. Not a huge deal. Okay, so now I have my carbocation, and I'm ready now to have a base take a beta hydrogen and finally be done with this problem. Okay. Now, we were given a very strong acid to begin with in water with heat. Okay. Now I have to decide what my base is in this problem. Right now my options are, I have water, which is amphiprotic. It's equally an acid or a base, so it's a very weak of both. But then I also have HSO4 minus, which I made over here in this step. That minus should tell you that this is going to be likely a better base than water. Okay? In that case, it is. So that would be the base that I use. It's going to come back and take that hydrogen back. Notice it doesn't matter which beta hydrogen I choose here. Either way, I'm going to be making the same molecule because this is symmetrical. So I can draw in a beta hydrogen here. My HSO4 minus is going to be my base. It's going to want that hydrogen back, create our double bond to get rid of our carbocation, and our major product will be with that in plane, because it's still trigonal planar, and we created our double bond there. Okay. Another disclaimer, these are my answers. This is not the answer key, but I do like going over this in the meantime. And if you catch something that isn't quite right when she is grading these, please tell me. That way I can make fewer mistakes going forward, and we both have a better idea of what's going on here, okay? These again are just my answers, but I feel pretty confident with most of them. These first few especially here. This one was, I thought, pretty tricky with the paraplanar going on here with the hydrogens and fluorine. But everything else is, again, not a guarantee is what I'm going to say. Just want to throw that out.